So, fine. So this is actually the is a Berhampur campus. You can see. Um, I would request those who want to visit, please drop a mail to me. We have a very small guest house, unfortunately, but we'll be hopefully be able to arrange for something. Okay, so today I'll talk about this generating of random Gaussian states. And Professor Panigrahi once told me that to make it as basic as minimum as possible. um, so let me start with the bare minimum. So as sir was telling that I actually came from the mathematics side, and for us, quantum mechanics is nothing but a non-commutative version of probability theory. So when you have a probability theory, what you generally get? You have three things. One is a sample space, a set of events, and a probability distribution. This is typically what we call as the omega, E, the set of events, and P is the probability distribution, or those who are more mathematically minded, they would say that it is a probability measure. So this is what is called as a Kolmogorov triplet. Now, the quantum theory is a non-commutative version of this classical thing, where the sample space is replaced by a complex separable Hilbert space H. The set of events, now there are a lot of troubles here, is represented by the set of all projections onto H. And what is most important is the probability distribution, which is our dear old friend rho, which is a trace class positive semi-definite Hermitian operator with trace rho is equal to 1. Now, often we are bothered about the case when the H is a finite dimensional complex Hilbert space. In that case, things are very easy because it will become like C to the power D for some where C is the complex numbers. That is the default product of the complex numbers. And rho, in that case, it will be positive semi-definite Hermitian operator, and trace of rho will be is equal to 1. Positive semi-definite means the eigenvalues are greater than equal to 0. Okay. I have also used the thing that P of H, which I am telling as the set of all projections, which is analogous to the set of all observables. This part is a little bit more complicated, but I don't want to go in it. But since there, I expect that there are a lot of students here. I should add that this is an interesting area of research. It was also 100 years ago, starting from von Neumann, and it is still today. It's an interesting area of research because of many things. It is all one is that it is also connected on the measurement theory, as which you know much better than me. And I am trying to do it, but it is not actually coming properly. Can you see the full screen, or you are seeing the side panel also? And more important, whether is it changing the slides? The slides are changing. Okay, okay, very good. Like presently, I am in the slide Premier to Quantum Theory, and next I have put it as Prelude to Gaussian States. Is it okay? I mean, can you see it? Okay, good, good. So the point is that this set of projections are also intrinsically connected with two things. One is the measurement theory of the part on that part you know pretty well, much better than me. And the other side is also you know better than me is the set of is the matter of quantum thermodynamics. In fact, studying the projections itself gave what in mathematics we call as the von Neumann algebra. and different types of fundamental algebras comes out of this area. So it's an active area, research area in operator algebra. But often from math sides, people forget about the physics, which why it came up. This set became so interesting and so important. So those who are students here, they may like to venture in this part because mathematics research is going in one direction, physics research is going in another direction, and they are all compatible, but there are not many people who can actually do this compatibility. Let us come back to the Gaussian states. Okay, so what is the major problem here? So for the Gaussian states, of course, the Hilbert space is actually a Fock space in mode. Let's consider it as an n-mode Gaussian state. So it will be gamma of c to the power n. How do I write this thing? So let us consider the position and momentum pairs as q1, p1, q2, p2, etc., qn, pn. They are position momentum observables. They satisfy the CCR relations. They are, that is a canonical commutation relation. And that means again that Qi, Qj is equal to is equal to delta ij. That means if I is equal to j, then it is equal to then it is of course commutes. They are the same. Otherwise, it is equal to 0. Same thing for p's and qi pj. If I and j are different, then it is equal to 0. But if they are the same, then you have this h cut I into h cut of into identity. Okay. The Heisenberg uncertainty relation also comes from there. Now, for this state's rho, let us assume that this rho has up to finite second moments. Okay. And I write the in that case, I can write that the covariance matrices, and I write this covariance matrix by A. Okay, and this xi, xj's are this qi, pj's, etc. in proper order. Now, of course, xi's and xj's are two observables. That means they are Hermitian operator. And if we go back to classical theory, then product of two random variables, two observables need not be an observable because it need not be Hermitian. But if I can just take x1, x2 plus x2, x1 divided by 2, then it is an observable, it is Hermitian. And that is how I can take the covariance thing and I can define the covariance. Now, this covariance matrix A, mind it, of course, this has to be well defined, and that's why I have assumed that this row should have finite second moments. Uh, then Heisenberg uncertainty relation will force us the following thing that it should satisfy the Heisenberg uncertainty, and this can manifest by this nice small matrix inequality that A plus I times j to k is greater than equal to 0, where j to k is the the k copies of this matrix 0, 1, minus 1, 0. Okay. Now for Gaussian states, I have an interesting property here. This covariance matrix is everything. Let us put it slightly different way. I said about the Fock space, but I have not defined the what is a Fock space. Um, so so consider a Hilbert space H is equal to c to the power k. Now I can define the bosonic Fock space in the following way: the direct sum of symmetric tensor products of infinite symmetric tensor products, and a state acting on this space is an n-mode Gaussian state if its Fourier transformation is given by this equation. You see now there are a couple of things here. First of all, there are this x plus iy. I would have this is this is a complex number would be there. It's a z which is in c to a power k. I can break it as the real part plus I times the imaginary part, which is here the x plus iy. This is equal to now this is coming with respect to three fixed quantities. One is L, one is M, one is S. So L and M can be considered as position and momentum mean. And S is the covariance matrix. As we have seen earlier, I used the notation A. Here I am using the notation S. This is satisfy this matrix, this nice matrix inequality. Okay. Now, a couple of things here. Of course, uh, why I have used a different notation? Because that matrix inequality which we had given, it will be satisfied by any state for which up to second moment is well defined. But for Gaussian states, of course, for which the second moment up to is well defined, this will also satisfy this same matrix inequality, but it has one interesting extra property. The property is that anything, whatever you want to calculate for Gaussian states, like entanglement, entropy, or any different version of entropy, or you want to apply a Gaussian channel on it, whatever you want to do, all these things are encoded inside this particular matrix. Well, I should also tell that this position and momentum means also play a small role, but most often this covariance matrix is alone, which takes care of everything. In fact, there is a theorem which tells the following, that if you have a real 2n by 2n 2k by 2k matrix which satisfies this inequality, matrix inequality, then corresponding to that matrix, you have a mean zero Gaussian state. And conversely, for any mean zero Gaussian state, you have a covariance matrix which satisfies this inequality. Okay. Now, whenever we talk about this covariance matrices, so what did I say? I said that this is a real symmetric covariance, a real symmetric matrix 2k by 2k which satisfies this matrix inequality. One simple observation is the fact that S itself will be a positive matrix. Okay, because if you take a complex Hermitian matrix, then it's which is positive, then its real part is also positive. So, and any case, by the way we have defined, this will also be a positive matrix. Now, it is real, it is symmetric. So it has all eigenvalues. You can diagonalize this thing, but there is a very interesting thing happens, uh, which is not the standard diagonalization, which is called as the symplectic diagonalization. And corresponding to that diagonalization, I get what is called as the symplectic eigenvalues. So consider a strictly positive real symmetric matrix A, 2n by 2n real symmetric matrix. This can be, sorry, it should be called as a K. I wrote the by mistake as N. So it can be diagonalized by the symplectic matrices. Yes. Hello. Hello. Am I audible? Sorry.
Yes,
Am
sir,
I
you are
audible, or
audible, sir.
have I lost the connection?
Sir, you are audible, sir.
Okay, fine, fine.
Please proceed.
Okay. Okay. So this will be diagonalized by the symplectic group matrices of the symplectic group. So symplectic group, you can define it in the same way that you consider the invertible matrices, and then this invertible matrices such that L, this any element L from this group will have this property that L J2K, L transpose is equal to J2K. So J2K is the kind of it is a centralizer of J2K. Okay. Why these things are important, why these things are interesting? Because all these terms, whatever I have said so far, I told it from the matrix or mathematical point of view, but all of them are coming from quantum optics. Those who have taken at least one course have definitely seen this symplectic group, how it comes, and the metaplectic group corresponding to that. And anyway, so this object, this diagonalization, here the diagonal elements will come in pairs. So like D1, D1, D2, D2 up to dk, dk. Okay. This diagonalization is very important because these diagonal elements are also, for one thing, they are called as the symplectic eigenvalues. And two, this dk's or dj's are related to the temperature associated with each mode. In fact, you can calculate the entropy of the Gaussian state by using these DJs. It's a simple formula there, but I am not going to in that thing. But what is more interesting for me is that about the entanglement. I said that this covariance matrix alone will give you everything whatever you want to do. So one is about we are getting the entropy. The second thing is we are getting about the entanglement. This is more interesting for me. Now you consider a two-mode Gaussian state, which is will be represented by a 4 by 4 covariance matrix S, real symmetric, strictly positive. What can I say? Of course, this 4 by 4 matrix will satisfy this inequality that S plus I times J4 is greater than equal to 0. Now, I want to check the entanglement. The entanglement is given by the very simple thing that S plus I times J2 minus J2 is also greater than equal to 0. So if that happens, then I call it as a separable, and otherwise it is entangled. So this is what is known as the Simon's criteria. And Simon's criteria is, I mean, it is given by our, many of our teachers, Professor R. Simon, in sometimes in 2000. It has something very similar to what we generally do for two qubit systems. Remember, for two qubit systems, the partial transpose is necessary and sufficient for separability. That means if a state remains positive under partial transpose, then the set, if a state remains positive under partial transpose, then that state is separable. And it's an on-leaf also. So if it remains, so both way. Similarly, here this criteria was found out by checking the partial transpose of Gaussian states, which manifests by using that single minus sign. I mean, this minus sign, you can put it on the first system also, a minus sign. Any one of them should be converted to minus. Okay. So, just like the qubit system, here also we have an interesting thing that this partial transpose or this Simon's criteria is a necessary and sufficient criteria uh, thing for two mode systems. So that means if a state, if a covariance matrix, if for a state S, if the covariance matrix satisfies this criteria, then it is separable. And conversely, everything which satisfies this is separable, and it does not satisfy this object, is then it becomes an entangled object. Again, there is an issue here, that is this is not a this is an one-way thing if we go for any arbitrary dimensions. That is to say that just like in the finite dimensional cases, you know that that C2 tensors C3 also, of course, there is this is a necessary and sufficient criteria. But if you take any other composite dimensions, then it is not any more necessary and sufficient. In particular, there are states which are positive under partial transpose, but they are entangled states. So similar thing happens here also in in other dimensions, that it is positive under partial transpose or it satisfies the Simon's criteria, but it is the state has been proven to be entangled. Though I must say a few things here, that here the situation is not as bad as in the finite dimensional cases. Like if you consider one mode versus n mode, then also with some extra conditions, this Simon's criteria remains as a necessary and sufficient thing. So there are a series of articles by Adesso where he worked on these things. But let us not go in that thing. Rather, I say exactly the this PPT entangled state, or also known as the bound entangled Gaussian states. So for that, I need a different criteria, which is again fortunately a necessary and sufficient. So let us write down the covariance matrices in the grouping, whatever we have done, that Q1, P1, Q2, P2, etc., Qn, Pn. Now I can write this object as, let us take it a M plus N mode, and I want to consider M mode versus N mode entanglement. So I can tell the following, that I can write down this object as A, B, B transpose C, the covariance matrix in this way. As matrices it will be. Now, if I can find out an M mode covariance matrix X and an N mode covariance matrix Y, such that this matrix inequality holds, then my covariance matrix S is actually represents a separable state, separable Gaussian state, and the converse also holds good. Okay. So in other words, here you have to have find out X and Y such that X and Y are correspondingly M mode covariance matrix and N mode covariance matrix. In other words, X and Y should satisfy that matrix inequality which we have seen earlier with a suitable value of K. Okay. Now this also gave us an interesting way to construct the Gaussian states, um, which are entangled, but which are positive under partial transpose, number one. And number two, because this is a necessary and sufficient condition, given an arbitrary Gaussian state, one can try to construct this X and Y by using some kind of a semi-definite programming. So this became very, very interesting and powerful tool for checking this Gaussian, this entanglement. Of course, it is an SDP, semi-definite programming. So you understand that things may not actually give you any result after several rounds of iterations. But to some extent, this is fine. You can sometimes you really do need to check it quickly that whether you can get some good results or not. And often this gives the result. Okay. Now, this is I said that this is a bound entangled states are also there for any arbitrary dimension. So this is an example of a bound entangled state. So by the way, this result is due to Warner and Wolf in PRL in 2001, in which they constructed this bound entangled state. You can show that this object, this is a two mode versus two mode. So eight mode state, it is a two mode versus two mode. And in this mode, you can show that this is a bound entangled. This satisfies the Simon's criteria, but it is entangled because one can show explicitly that there does not exist any X and Y such that this matrix inequality will hold. Okay. Now let me come to my own talk. These are all background informations. So what I was always bothered about the fact that there are not many examples of bound entangled Gaussian states. Often, of course, if you go to Warner and Woolf's paper, they gave a recipe to construct a bound entangled Gaussian states. And with that recipe, they have given one such. But I kept on always considering that, well, can you do one more in the same thing? Well, of course you can do it, but if you see the literature, there are hardly any examples. Whenever somebody gives that, can you give me a bound and tangle Gaussian state? Well, yeah, you take the Warner and Woolf one. So I was always a little bit bothered that there are not many examples of such things. So is there a way to generate a lot of examples? Okay, fine. So that was my first motivation. Now the second motivation takes a little bit. I have to tell a little bit more about the thing about symmetric extension of states. So what is known as a symmetric extension? So forget about any Gaussian states. Okay, take any Hilbert space H a tensor HP. I have a state rho. I say that this object is K extendable with respect to system B. If there is an extended state rho tilde, which belongs to HA tensor K copies of HB such that two things holds. Number one, among those K copies, if you take any permutation, this rho tilde remains invariant. And number two, you kill any K minus 1 copies. That means you trace out any K minus 1 copies of HB, you get back your rho. Then I call this as a symmetric extension. Mind it, this is for any state, any finite, infinite, whatever it is. Now, question is that can you say that whether a state is extendable or not? Well, very difficult question, of course. And if a state is extendable for any value of k, I call it as a completely extendable thing. Now, let us see what happens for Gaussian states. Okay, I should say here one more thing that there is a result by Dohet for finite dimension. There is a result called by Doherty, Plenio, and somebody else actually. But this is not a very original research because the same thing was done in much more detail in sister algebra in the year around 1998 by three mathematicians. Uh, for finite dimensional sister algebras, we have had they said the following thing that a state is completely extendable if and only if it is separable. But what they could not do is proper thing for an infinite dimensional Hilbert space. Okay, so let's go for the infinite dimension or at least Gaussian situation. So if I have an extension in Gaussian case, so what will happen? Okay, of course, I would have something like the bound and I use the same notations like A, B, B transpose C. A is an M mode, that is 2M by 2M matrix. C is an N mode, so 2N by 2N matrix. And the whole thing, this matrix will be 2 into M plus M, N. Okay, so I can say that it is a K extendable in that in the second system. That means the this gamma of Cn side. If I can find out a theta matrix such that this extension object Sk is the covariance matrix of the Gaussian state. Also, that means it will satisfy this Sk plus I times J2 M plus Nk is greater than equal to 0. Okay. Now, this is our result. This was a result long before by myself, Professor Rajaram Bhatt, and Professor Patsasarathi, that a Gaussian state is K extendable if there and only if there exists a theta such that this matrix inequality holds. That means this is theta is sandwiched between C plus I times J2n and B transpose into A plus I times J2 M's inverse into B. So if you can see, this is a, instead of putting an in minus one, I have written a just a minus sign. It is there for a technical reason. It is the Moore-Penrose inverse. See, the what may happen is the following, that your A plus I times J2M may not be an invertible matrix, but but it has a subspace in which it is an invertible matrix. So take it inverse on that subspace and keep the rest of the things as it is. This is what is called as the Moore-Penrose inverse in matrix theory, and that is it. Okay. So this was a result which it was an if and only if result, as you can see. And we have also have shown that any separable Gaussian state is a bipartite system is completely extendable, and conversely every completely extendable Gaussian state is separable. In fact, actually we did the general result for any arbitrary states need not even be it need not even be Gaussian. Also, this result holds with a small requirement, that is at least one of the sisters dimension should not be two other of the bipartite situation. Okay, but let us first stick to the Gaussian case. Now, What we had done, actually, what after this result came up, there was an extension by Andreas Winter, Gerardo Adesso, and Ludovico Lamy, where they had considered this simple question that what will happen in the case when my extension is only up to the level k, but not up to the level k plus 1. A very natural question. So they modified this inequality. I'll come to that question a little bit later. And so at this point, I can tell my second important motivation for this work. I wanted to know what is the extendability limit of the PPT entangled Gaussian states. Can they be only one level extendable? Because the example which we had seen earlier, this is extendable only up to level 1. That means it is not at all actually extendable. So who knows? I mean, it can very well be possible that all Gaussian states, there is no different levels of extendability, in particular for PPT entangled states. So this was a question which we thought worth asking, but then is that a way to generate Gaussian states? How to generate states? So now there is an important thing about how to generate states. So um, this is actually done in the following ways. Just give me a second. Yeah. So I made a slight mistake here. Let us consider the finite dimensional case. So I have put the slides in a slightly wrong place. Sorry. So consider finite dimensional systems. What are you going to do to generate a random state? There are two ways. Number one, take a random pure state shell. Okay, in a Hilbert space H where you want to get tensor with an auxiliary Hilbert space, which you are going to get rid of it. Well, you have many ways to generate a random vector. And then if you have generated a random vector, you can just normalize that thing. It will give you a pure state. Take the pure state and then take get rid of that auxiliary system. So you will get a mixed state, and that will be a random mixed state. Okay. The moment you trace out the auxiliary system, you get a random mixed state. The second method of generating it is actually by using you. Why do you bother to generate with a pure state or a random vector? You generate a random matrix. The only problem for generating a random matrix is that okay, you may get a random matrix, but that matrix may not be positive semi-definite. But you can multiply it with its dagger. That will be always a positive semi-definite matrix, M into M dagger, but it may not be trace 1. So you divide it by trace of the whole thing. Then it will get your state row. Okay. So these are typically the two different ways to generate random states in finite dimension. What happens for Gaussian cases? Well, we are not the first one to look for the random this generation of random states. The first this object was achieved by two persons, this Fukuda and Koenig. They thought about the following problem thing, that let us consider the k mode situation and n minus k mode environment. And let us consider a pure Gaussian state bounded by a compactness criteria. That means this Gaussian state will have kind of this. There will be a energy bound of this Gaussian states. That is where the Hamiltonian H is given to be the summation of the position the quadratures, and you fix your E, you get your you can generate that. Now this object can be diagonalized in a passive way by taking the orthosymplectic group, that is the symplectic group intersection with the orthogonal groups. And I can take this object as this Zn direct sum of Zn inverse, because so actually what happens is that that any pure states of the any pure Gaussian state can be written as L into L transpose, where L is a symplectic matrix. The problem happens here is that because L is a symplectic matrix and because L is these symplectic matrices are non-compact objects, so you cannot really define a random Haar measure on that thing. Unlike for the for the for the finite dimensional cases where things are slightly easier, because you can define a random, you can define a Haar measure, you can do a random sampling. Here, symplectic matrices cannot be, you cannot do a random sampling on symplectic matrices, but if you take the orthosymplectic group, then you can do a similar, which is the largest compact subgroup. There you can define a Haar measure and you can do a sampling. It's a slightly technical matter. So which means you can actually take any Gaussian states, pure Gaussian state in this HA tensor HP as a LL transpose. In particular, you can write it in terms of an orthosymplectic matrix, a diagonal matrix where the elements are kind of Z, Z1, Z1 inverse, Z2, Z2 inverse, etc. And then that orthogonal matrices inverse or transpose actually. Now these Z's, Z and 1 by Z, this will actually give you the Hamiltonian, and you can from there Hamiltonian will give you kind of an energy bound. So that it take that energy bound, take using that thing, you kill the extra dimensions and you can get a K-mode Gaussian states. Okay. So initially it was done by Serafini, but Serafini and others, but this was further polished by Doherty, by a person, Fukuda and Koenig. Okay, in this 2019 paper. It's a bit clumsy, but the good part here is that you get several, you can actually generate the random Gaussian states by using that. Of course, you have to put an energy restriction on that Gaussian states. So what is the problem here? Why not we use this thing to generate random Gaussian states? The problem is that when Fukuda and Koenig did this work and we had gone through the calculations, the states which we are getting had had some very strange criteria. For instance, their entropy was becoming almost like a delta function, and their density, they were kind of having a density such that we were hardly getting any PPT entangled states. So we got a feeling that maybe this is not the right way to generate the Gaussian state. Of course, it is physically meaningful. It is very much physically meaningful, but this was not giving us enough PPT entangled states. Okay, and forget about extendability. It was not giving anything. Okay, so let us have a different way to generate it. So one more way to generate it is now, as I was telling, that Lamick-Shatsky and Editson's thing. I'm sorry, it should have come up earlier. So this was the thing which we had represented by theta. I am they represented by delta, and they had a slight different inequality. And this was the thing which we are going to use in this whole result. Okay, fine. So let us come to our actual calculation. I can just ignore it. So what we did the following. So we wanted to generate a covariance matrix, 2n by 2n real symmetric covariance matrix satisfying the condition S is greater than equal to I times J2n. Okay. Now, a random covariance matrices I wanted to be defined as an element of the Gaussian orthogonal, what is in the random matrix theory, which is called as the Gaussian orthogonal ensemble. Okay. And the every element will be taken in the Gaussian with a Gaussian distribution. And I say that a random symmetric matrix is said to have a GOE of n comma sigma if the random variables, each term is independent. The diagonal entries have the distributions with mean 0 variance 2 sigma square, and off diagonal entries will have the distributions as mean zero, variance sigma square. Okay. Now we get on the space of real symmetric random GOE matrices with sigma is equal to 1, I can get the distribution as in this following thing. And here we also the moment we say about the Gaussian the random distributions, we also have to check for the Wigner's distribution where you had a semicircular law. In this case, if I take it in this particular way, then I can get also a semicircle distribution for the covariance matrices which we have defined. Okay, of course, it is. Let me skip these sites because this is going towards the matrix towards the mathematical thing. But what I can assure you is that if I can take a random matrix taken with a Gaussian orthogonal ensemble distribution, then what we do is we shift the matrix to a reasonable amount such that the shifting, that is the g plus lambda max of I j2n minus g times identity, this object will be a Gaussian matrix. How do I do it? Because we have a G, and I know that I know my covariance matrix should be greater than equal to I times J2n. Now I can take the G minus I times J2n minus G. What should be the maximum eigenvalue of that thing? If I can shift that part, add identity with it, then we are through. Okay. And this is take it from me that this will be a random Gaussian matrix, and in this case the minimum eigenvalue of this is g minus I times j2n, because that will be my that inequality has to be satisfied. The minimum eigenvalue has to be equal to 0. Okay, so that means I can safely say that this SG, the way we have chosen the matrix, must be greater than equal to I times J2n. In other words, it's a random matrix. Okay, random Gaussian covariance matrix. This random covariance matrix is invariant under the passive transformations. That is, if I take the elements from the orthogonal state matrices intersection with symplectic matrices, then these objects will be invariant. This is necessary because to show that this object is truly invariant with respect to some compact group. Number two, that if it is a random covariance matrix, then its M mode marginal will be a shifted cover distribution. Then let me skip these technicalities. Rather, these are more on the random matrix type of thing. What is interesting is the following, that I this guy if I sample these objects, then there is a way to sample them properly, and I can get a lot of random Gaussian covariance matrices which satisfies the PPT criteria. In particular, uh, uh, just for a one single thing, that these objects will have an entropy also can be plotted of this. This is about the purity of the states I can calculate, and this is in the part which I want to come, that I can take the numerical histograms in this case of n is equal to m plus m modes separately, and I can show that there are a lot of entangled states. In fact, we had gone up to 50,000 samples for different this sigma is equal to 1, sigma n is equal to 10 to sigma for many different values of n and sigma. And in every cases, I was getting the PPT, this areas are the PPTs, and these objects, these sites are the pink parts are the non-PPT objects. This clearly shows that compared to the result by the Fukuda and Koenig, where everywhere we were getting kind of a delta distributions. I didn't put the plots, but but we also have done that calculations where we were hardly getting any PPT entangled states. Actually, we didn't get any PPT entangled states. By using this kind of sampling, we had a lot of We have managed to generate several PPT entangled Gaussian states. Not only that, these states will have different levels of extendabilities. You can see that this is the K is the extendability thing. So we had plotted that how many for each cases we have plotted how many what are the level of extendabilities of different things. So we went up to 50,000 samples for when we have n is equal to 10, and we had up to 400 for when n is equal to 100. As you understand that we had a computational limitations. So what we have done so far is, let me summarize it. Number one, we have found out a different way to generate random Gaussian states. With this random generation of random Gaussian states, we have found out a way to generate PPT entangled states. With these PPT entangled states, we also have shown that there are different levels of extendable states. Okay, there are different levels of extendability, and we have given a plethora of examples of such objects. And as I can see that probably this is the first such work where the PPT entanglement and the extendability were exclusively and exhaustively calculated for the domain of the Gaussian states. So I complete the thing here. So this is our group uh, of right now, and these are the authors of the paper. Taiko Hainosari is the only other person, and this is supported by DST as well as NRS. So thank you so much. Okay, questions?
Brother. Now we are open for questions. So, Ritabrata, let me start. See, for example, this random matrix theory, which
Hmm.
was earlier studied by, this nuclear physics people and, it's typical uh, random matrix theory. In what way
Yeah.
these results supplement the same, or how much was it known earlier? For example, PPT, they did not know. For sure, they did not know PPT and those entanglement for sure. So that means
Yes.
your results are really supplementing them. Can you elaborate a bit more?
Okay, so the thing is that if you consider for the pure for the finite dimensional cases, you know that random matrix theory has quite a lot of uses for the channels and the states, right? Many of the properties have been checked. Okay, in this
Yes.
case, the problem was the following: that the PPT entangled states we knew. But see, in random matrix, what we generally look for is that whether there are a lot of examples that possible or not. Of
Right.
course, there can be infinitely many objects that are possible. Say, for instance, consider the set of all pure states. Okay, but if you could look at the set among the set of states, then it's a set of measured zero. Of course, there are infinitely such situations are possible. But what typically we look for are the cases in which there is a sizable amount or a volume of the states for which you can do the sample. Unfortunately, for the PPT entangled states, there was no good way of sampling. The earlier results, mostly by this by the which actually culminated to the paper of Fukuda and Koenig, they did it in a more physically sensible way. But if we use their techniques, then most of the things whichever we wanted to check, there we were getting almost nothing, which is kind of expected because their sampling was more towards like a delta distribution kind of thing, Dirac delta distribution type of thing which it was coming up. So the question which we were worried was that um, it may be possible that there are a lot of PPT entangled states, but they may be a set of measured zero in the set of the Gaussian states. Okay, is it true?
And so, I doubt, eh?
So, so here what we have done the work is that no, it is not true. It is actually due to the sampling what the other people were doing. We are getting this kind of things. Two, by taking these random Gaussian states, now we have a plethora of examples of PPT entangled states of Gaussian states. I mean, PPT entangled Gaussian states. So typically, when people looked for a PPT, they such states, they used to go for this, Warner and Rules paper. But now they can actually use run our codes, and then those codes can give you the new examples as well. Okay,
Okay. Yeah,
and
yeah,
with
okay.
different degrees of extendability. This the last one became important because recently many of these optimization techniques actually work on different this extendability helped them help people in particular those who are in STP and those who are in working in complexity theory. They use this STP often on various results, various kind of optimizations. So there was no such good optimization for the Gaussian cases. So we also have defined a tool for this kind of things.
Thank God. More
Was there?
questions? Yeah, more questions. Well, if they are not asking, let me ask you. I see.
Okay, sir, sure.
Now I'm became more ambitious. For example, random matrices came to nuclear physics in the context of
Yes,
nuclear spectra, right? So
yes,
there, disparity, time reversal, that is how, they characterize the nucleus and corresponding spectra. It threw a lot of light on the complex spectra. Similarly, the
yes.
final thing what you have introduced, I'm sure if you look at it properly, it will throw light on the physical system. Have you thought about it?
Yes, we were actually working on it, but we are thinking seriously. Let me put it in this way. But there are many things which needs to be done in this area. As you know, sir, the major problem here is that what we understand right now is that probably we have to go not only to the Gaussian but also the non-Gaussian domain also. Okay, maybe keeping up to the second moment well defined. Then we expect to get we can expect to connect it with the optics much more properly. Let me put it. Yeah. In fact, I think Arvind had recently written one paper, and he was trying to do the same kind of things, with optics, and again with that. And he also cited our work for generating of random Gaussian states.
So it's very powerful, very useful method. Yeah. How about,
Thank you.
yeah. Any more questions? So if not, there's time, Ritabrata. So again,
Thank you, sir.
yeah. And you are really
I
invited
hope I
to
will be able.
come.
Sure, sir. I hope I will be able to host you also sometimes
Thank you
when
so
our
much.
things are a
Yeah.
little better.
Thank you. Okay. Bye now.